All right. Hello, everyone. Thanks for having me on today. So far, the talks have been absolutely stunning. I've had a blast and learned a lot. And today, I want you to put your fanciest horn-rimmed glasses and drive over on your fixie, and we'll get really hipster and talk about bespoke, artisanal Swift static analysis. It's something that you can handcraft yourself with lots of love and care. Well, before we dive in, it kind of sounds like a complicated topic, but there's this fantastic person. I encourage you to follow him. He's a renowned compiler expert, and he recently shared that, as far as he knows, there's really one kind of canonical source for what is static analysis. And so he shared this paper. And so I started digging through the paper, static program analysis. And I'm like, okay, well, how hard can this be? What is static analysis before we dive in? It turns out that static analysis is the art of looking at your source code, looking at your program without actually running it, and trying to assess certain properties from it, trying to assess certain behaviors from it. Is it buggy? Is it fast? Is it slow? Is it doing the right thing? Is it probably correct? And it turns out that there's this whole field. It becomes extremely technical, but I was diving into it saying, well, how hard can this really be, right? And so I started reading it, and it turns out it was pretty straightforward. It just talks about concepts like interprocedural control flow graphs and lattice theory, monotonicity, and constant propagation analysis, and very busy expressions, and transfer functions, and closure analysis for lambda calculus. Okay, maybe I'm not as prepared as I thought I would be diving into this topic. All right, well, all I want to do is write better code by getting more information out of it. And so I started reading this paper, and I was just like, I have just as much chances of writing real static analysis as this guy does getting his car washed. Like, sure, maybe you'll get the car a little wet, but you'll be soaked and you'll be bruised and busted and bleeding by the end of it. And so, okay, let's start over. Is there maybe a better way that I can be doing this? Do you have to be a compiler wizard in order to just get a little bit more information out of your program? And so for inspiration, I turned to this really old programming language that some of you may have heard of. It's called Objective-C. And for anyone who's written some Objective-C before, you're probably familiar with, especially in Xcode, with the Command-Shift-B command, which runs the Clang static analyzer. Ooh, sounds magical. It is magical. It catches bugs in your software without even having to run it. It's a programmer's dream. And so I started looking up the Clang static analyzer, which is entirely open source. I'm like, great. I'm just going to have to copy some code over, maybe translate it from Objective-C or C or maybe even C++ to Swift, and then I'll have Swift static analysis. So I started looking this up, and it's this really wonderful set of tools. It's built on top of Clang, which is a C language compiler. It's built on top of LLVM, and so this wonderful compiler infrastructure. And so I start looking at this, and I'm like, yeah, like Swift is basically the next direction from Objective-C. So presumably there's a lot of this that it will apply. So I start looking at, all right, well, if the Clang static analyzer is built on top of Clang and LLVM, well, what are the equivalents for Swift, right? Well, the Swift compiler also uses Clang, and it also uses LLVM, and has a few other layers on top of that. It has, of course, the Swift compiler itself, and it also has similar tooling that Clang does, and the LLVM infrastructure. And so just like there's libclang, well, there's SourceKit, which is a set of tools that you can use to kind of interact with that really powerful, really deep compiler infrastructure under the hood. But if you were to build this correctly, in the same way that the Clang static analyzer is done, you would probably need deeper hooks into the compiler. You would need to write this in C++. You would need to be very familiar with this pretty arcane, hard to understand, requires a PhD in compilers logic that was shared in that paper that I shared just a little earlier. You'd have to write this in C++, and you'd need to be very familiar with concepts like control flow graphs that I mentioned briefly earlier. So I started thinking, there must be another way. Can there be another way? And maybe it's not as powerful or as academically correct, but all I want is to just know a little bit more information about my source code and write better code. So I was thinking, what if it was possible to kind of make a few trade-offs, but find a way that wasn't so complex to build it? Is it possible to build something like static analysis, which again is the art of getting information about the behavior and properties of source code without actually running it? So is it possible to build something like that that's simple to build, that's fast to build, right? Where you don't need to do a ton of boilerplate dance and song and dance in order to make this happen? Can it be easy to run where you don't need to build a whole fork of the compiler, which, if anyone's tried building a Swift compiler, takes a few ages even on a fast machine? And most of all, is it possible to do this without having a PhD in compilers or deep knowledge of C++ or the internals of the Swift compiler? And that's where we get to what I call this bespoke artisanal Swift static analysis. It's basically a poor man's Swift static analysis. So going back to the basics, what do we need to do? What are the ingredients of a static analysis pipeline? Well, you need to be able to run over your source files that you want to analyze. I think that's pretty straightforward first step. Next step, you need to be able to perform actions on all of those source files. Easy enough, right? You don't need a PhD in compilers to understand this. Okay, now it gets tricky. We need a way to get detailed information about the source, semantic information that usually only the compiler knows, information that would be hard to infer if you're building tooling on the side, kind of re-implementing what the compiler does. Okay, so we need detailed information. Okay, I'm not really sure how we can do this. We need a way to extract some of the interesting results that come back from this detailed information, right? Because you can have a ton of information. I mean, the Swift compiler writes a ton of files. It has a bunch of all of this information, but if you can't act on it, if you can't translate that to something that's useful to use the programmer, it's not very useful either. You need a way to report them back to the user of the tool, and you need a way, ideally, to act on the results, right? If, for example, you find code that needs to be corrected, then ideally the tool should be able to do it itself, right? You shouldn't have to have these manual steps if the compiler is smart enough to do them for you. All right, so this is where we start to look at something that's probably familiar, at least some of you. If you look at SwiftLint, which is a tool that can do actually most of what's in there. It's a linter, right? Typically, it acts on the pre-type checked AST, right? So it acts on the source code without all of this deep knowledge about how your app is built, what all the other source files are, which is great because it means it runs quickly and it runs easily, where you don't have to pass it compiler arguments, you don't have to run the compiler and things like that, but it has limitations. It can get us most of the way there. It can actually kind of provide a baseline for us to at least kind of get those steps out of the way, right? A way to run over your Swift source files, a way to perform actions on all of these sources, right? How SwiftLint works today, it runs these analyzer rules, or these lint rules, rather, on all of your source files. It doesn't get you that detailed information to the level that we need for static analysis, and it certainly doesn't give you any of the means to extract interesting results from it, but you can report them back to the user, right? Either on the command line or in Xcode. You'll see some errors or warnings, and a way to act on the results where you can auto-correct some of the correctable issues. All right, so what's left to do? All right, so now that we've kind of found a tool that we can build on and actually do the hard work, the static analysis part, we need to figure out a way to get that detailed information about your source code. And then after that, you need to take that information and turn it into something actionable. Easy enough, right? it's at least easier than trying to understand all of these academic concepts about traditional static analysis. So this is where we get to SourceKit. I mentioned it briefly earlier. It's kind of a window into some of the internals of the compiler from the outside without having to build a whole new version of the compiler. The Swift compiler doesn't really have an extensible plugin architecture. You can't really say, all right, thanks for the Swift compiler, I'm going to add this step in between. You can't really do that. It's not built that way. And so instead, Apple's provided this tool that lives on top that can kind of access some of the internals of the compiler and give you some of the same information that your IDE gets. So Xcode uses this, for example, for syntax highlighting or for even richer information about your source code. So there's a few interesting requests that SourceKit can operate on. The SourceKit operates on a request basis. So you basically have SourceKit running, you start a daemon for SourceKit, and then you can ask it questions. You can say, all right, if I have the Swift file, what are all of the syntax tokens in it? Right? And then you get syntax highlighting information, or you get the pre-type checked abstract syntax tree. You basically get the shape of your program without all the symbols being resolved and saying, oh, well, this function called A actually calls into this module that's in this file, right? So that's the editor open command. This is what Xcode calls into SourceKit when you just open a Swift file. So this is a good starting point. It gives you information about your program, but it doesn't give you that detailed information that you need. So there's two very interesting calls, especially for what we're trying to build here. There's the index request, and there's the cursor info request. So the index request, these two requests actually require compiler arguments. And it requires the compiler to have already gone through the source code and built the program, effectively done the type checking phase. This is the phase after the parser and the lexer where the compiler goes and says, okay, well, this is what all these symbols mean, and they exist, and they're linkable, and they're existing on this platform. So these commands need these compiler arguments because it needs more context than just the raw string text that's in your Swift file. It needs more context. It needs to know what all of your dependencies are, what the target platform is. It needs all these things for the same reason that the compiler needs to know these things. So it's a little bit more complex. But with the index command, actually, let's start with editor open. Say this really simple Swift file. You have a struct with a function in it. So don't necessarily try and read this. It's a little hard to read on the screen, but it's just to say that making this request gives you a few really useful tidbits of information out of it, and I've highlighted a few here. You can tell that the general structure of the program. You have a struct with an instance method inside it, and the instance method is B, and the struct's name is A. Simple enough, but you don't have some of the really useful information that we would want to use here. You can't really say, like, uniquely reference one of these, let's call them declarations, and say where they're used, or say where they're defined if it's a reference to some of these functions or types. But still, it gives you a general sense of how the program is shaped. Okay, so this is useful info. If we look at the request, or the index request with this same file, you can then get a little bit more information that you can then kind of stitch together with this editor open request, which gave you the shape of the program. And now with this, you can get a few more useful information. Like, for example, this USR key that's in there that kind of looks like gibberish. Well, that is called the unique symbol resolution identifier. Basically, just think of it as a unique representative ID for that particular declaration. So we have that for the B function and for the A struct. Okay, we're starting to get to something useful here. Finally, we have the cursor info request, which is the exact same request that happens when you option click something in Xcode. Say you want to see its documentation. Say you want to navigate to it. Xcode makes a cursor info request. And if you make this request, you'll get even more useful information. Here you have that same USR, the unique symbol resolution identifier. You have the type USR. You have the type name, right? B is actually a function that takes an instance of A, which is our struct, and returns void, and then that returns void. So this is basically under the hood how Swift does its currying, right? Where a.b is a function where it takes in an instance of a, and then you can call that function as b. So this gives us some useful info once again. You can say where it is and all that, right? So with these three different requests, we can actually start to stitch together some of that detailed, useful info that we want to act on, that we mentioned earlier. Now, we're getting a ton of info here, and we're not still quite sure how to extract some interesting results from this information. So this is where I'm going to give you a few examples of some of the static analysis rules that you can build using this kind of approach to do things like finding dead code. So dead code, why do we want to find dead code? Why is that important? Well, dead code is code that is unreachable from your app, effectively. And the reasons why you'd want to find this, there's a handful of them. One is it takes more time for your app to compile if you're compiling a bunch of code that you're not even using. Okay, so this is problem number one. Problem number two, you might think, or your intention might be to use this code, but you might have, say, copy-pasted the wrong thing and then forgotten to actually use that code. So that could be a bug. It's very important to find these bugs. And this is where static analysis really shines. It can give you these kind of superpowers on understanding your code in a way that your eyes just kind of might glaze over as a programmer. And so in this case, we have two structs, Fika and Bagel. They each have an eat function. And today we're just eating Fika. We're not eating bagels. So in this program, we're creating an instance of Fika, we're eating it, and just so that we can reference that bagel type, we're printing it. But we never eat a bagel. Right? So this might be a bug, or it might just be slowing down your code. Of course, this is a contrived example. Odds are, in your real apps, you probably have hundreds of these examples that you think you might be accessing, but you're not, or it's code that you've refactored out, but you forgot to delete the initial source, or things like that. So in reality, it can be a little bit more complex. All right. So the general algorithm for taking those sets of requests that we were mentioning earlier about getting useful information, getting detailed information about your code, we can stitch them together. Right? Finding dead code can really just boil down to saying, okay, well, what's all the code that's declared? Right? These are function declarations, struct declarations, type declarations, etc. What are all of the tokens, these declarations, what are all of the use cases, all of the usage points, right? And we call these references to declared code. You subtract one from the other, right? So everything that's declared minus all the stuff that's actually referenced, which is used, gives you the stuff that's unused. Easy enough. And because you have these identities, these identifiers, these unique identifiers for all of these declarations, it's easy to know for sure that when you find that bagel eat function, that's actually the one that's not used and not the Fika eat. And this is where static analysis really shines, because building this with just string parsing would be extremely challenging. And of course, these are simple examples, but you might have overloaded functions in your Swift code that some of them are used and some of them aren't, and they return different types, but at the call site, they look the same. So this is where static analysis is extremely helpful. So in this case, with just these handful of lines of code, we can then extract interesting information out of it. Like this bagel eat function is unused. Now, there's a few gotchas. When I started writing these rules, I started realizing that there's a lot of valid Swift code that is never directly referenced. Right? And this is where you start getting into traps. So, for example, if you look at this weekday enum, we have Monday, Tuesday, Wednesday, Thursday, Friday, you never explicitly reference one of these, but the fact that they all exist help you do things like you can create an instance of this weekday enum from a string and know if it's a valid weekday. You would never actually write this code, but it's just kind of a contrived example. So this is a case where this static analysis needs to be a little smarter, or you need to be willing to encounter some false positives. In this case, for this analyzer rule in SwiftLint, I've just declared all enum instances or all enum members I just ignore them when I'm detecting unused code. All right? So these tools have limitations because there's some tricky things to build out. There's a number of other cases, right? Dynamic code. Say you have IB outlets or IB actions or @obj_c annotated functions. Well, you might never be calling those directly, but because of the dynamic nature of these calls, they might still be used. So SwiftLint also kind of ignores those. Or protocol conformance code. Say our bagel and Fika conformed to the food protocol, and you never actually ate a direct, concrete instance of either of them, but you only ever accessed it through the protocol, well then those functions might come out as unused. So this is a case where there's false positives. And this is a trade-off. Almost all static analysis can't necessarily catch all cases. The trick is, can it be useful enough that even with the false positives, it's a useful tool to use? And I think the answer is yes. One last example is, again, with the unused theme, when you have imports, or when you have a complex application, like in the case of Lyft, the company where I work at, where we have close to 100 different frameworks or modules within our apps, it can be very tricky to balance the dependency graph of that complex application. And so reducing any unused dependencies and imports becomes extremely important for things like simplifying your code, simplifying your dependency graph, speeding up your compile times. So in this case, again, a contrived example, but you can imagine a function that you declare in your code that has a similar function declared in one of the Apple frameworks, for example. And in this case, the dispatch main function. Here, we're not actually calling the dispatch main function from the dispatch framework, the GCD framework. We're calling our own version of it. And so that would be an unused import. So there's a rule for this analyzer command that will find, first, we find all the imported modules. Right? So if we make this cursor info request to SourceKit, like we mentioned earlier, we can get information like what this module name is. Okay? So here we know that we've imported the dispatch. So you run this on your file, you know all the imports. Next, you find all the referenced modules. Earlier with the cursor info, I mentioned that you can tell if it's a reference or a declaration. So in this case, you can tell all the modules where all of your referenced declarations are coming from. Right? So if you were to make a cursor info request on the dispatch main from the dispatch framework, you can tell that it comes from that. But in our case, we're calling the one that we declared in our own source. So we could tell, once again, by listing through all the imported modules and then subtracting all of the used ones, we know what unused modules we have. So there's a few challenges here too. Operators currently can't be queried for their USR, for their identifier. So if you're importing a framework and all you're using it for is an operator overload, then we won't detect that. That's a false positive. And then transitive dependencies too. So say you're importing UIKit, but really you're only using foundation, which is transitively linked, right? UIKit links foundation. Well then, the automatic acting on these unused imports might not make your code compile, right? Because we're removing the UIKit import, but then you're missing a foundation import. So there's a few issues with this as well. Just things to keep in mind, trade-offs when you're using tools like these. So to give you a sense of how you would use this, because this is built into SwiftLint, you just declare what analyzer rules you want in your SwiftLint configuration, and then you run SwiftLint analyze, and you pass either autocorrect flag if you want it to act on the things that it finds, and you pass the log path to the Xcode build log results. Now this is a little tricky, and this is because these requests that I was mentioning need access to the compiler arguments to get your code to compile. Right? So this is a little unwieldy to use, but I think the value that these kind of rules provide makes it worth it. I'll give you a concrete example. For Lyft, we have about 4,000 Swift files that make up our driver and passenger apps across, like I mentioned earlier, close to 100 different modules. Recently, with a code base like that, you have lots of people constantly working on it. You're bound to find dead code. You're bound to have unused imports and, more importantly, unused dependencies that can really bog down and complicate your dependency graph. So I recently ran this tooling on our code base, and we found close to 1,400 imports that were unused. This is massive. This is a huge, huge number of imports. And it goes to show that even with experienced programmers working on a large code base, these issues do creep in over time. But not only that, but when we removed all of these unused imports, it was then very easy to tell which modules were still requiring or had dependencies on modules that weren't imported anymore. So we could actually get rid of 70 direct dependencies that we removed as part of this process. Again, simplifying the dependency graph massively. Now, if you do this, and if you run this kind of tooling on your team, I guarantee you that your entire team is just going to do a little victory dance. Like, everyone loves deleting code. It's way more fun than writing code. So this is really just scratching the surface. There's a handful of other rules that are already implemented, but there's a lot more that can be done. This is kind of why I'm talking to you about this today, is that I really hope that as a community we can start building more and more of these useful analysis tools. Things like finding inefficient code patterns or converting some of the sometimes buggy iteration code into more functional code that can be optimized by the compiler even more. Or you can even do things that are bespoke and artisanal strictly for your project, even if it doesn't generally apply to the community, like enforcing specific code architecture. If there's certain patterns that you want to encourage in your own app, I encourage you to create these kind of analyzer rules and share them in the open so that others can kind of learn from that and maybe derive something that's useful to them as well. And then finally, there's also kind of a more powerful type of linting that you can do where just working on the pre-type check AST isn't enough. And you need some deeper information. Things like enforcing explicit or implicit references to self or removing superfluous type annotations, things like that. All right, I want to wrap up by saying that, looking at these handful of rules that I shared, it's really not rocket science, right? Unused code is a matter of finding all of the declared code minus all the used code, and you find your unused code. Same thing for imports, right? So you can build simple rules like this that are extremely useful. Tools are just apps, all right? This is something that a colleague of mine recently kind of discovered. Of course, it seems tautological, but it's something that until you have that eureka moment and you say, use the same language to write tools as you do for your apps. Use the same kind of algorithms, the same kind of thinking. Xcode may be closed source, but there's a ton of the stuff that it relies on that is open and part of the Swift compiler or part of other projects. So I encourage you to not see that as the barrier to building tools like this. And finally, I think we have a bit of an issue in the Apple development community where we kind of rely on Apple to provide our tools for us. And when you look at other language communities like Rust, JavaScript, you name it, most of those communities build their own tooling. And of course, building tooling isn't for everyone, but I guarantee you that a lot of people in this room are interested, just don't know where to start. So hopefully this presentation was useful to that. Thank you very much for listening.